Welcome back, everyone. Thank you for being here and close to on time. I think your taxi reservations will be okay. So with that, I predict that we'll have a fabulous talk coming up. Śpiewak does not only organize fabulous conferences, he does fabulous mathematics, and he will tell us about this prediction of dynamical systems from time-delayed measurements with self-intersection.
Thank you very much. So indeed, no worries, all the taxis are safe, and there will be no announcements during this talk. Instead, I will talk about the theory of the so-called time-delayed embeddings of dynamical systems. And the key phrase in this is the so-called Takens embedding theorem. And the general scope of things which this Takens theorems, because it's actually a group of theorems proved by several authors in many categories, what they deal with is the problem of reconstructing or modeling an unknown dynamics from measurements performed via some observable. So think of a situation in which there is a dynamical system, but in consecutive time units, you don't have access to its actual states. What you have instead are values of measurements. Maybe there is some parameter in your system which you can measure, and as time goes by, you see the values of this parameter. And now the general question is how to try to, well, reconstruct, approximate, model this original unknown dynamics from this partial information that you gather. So I guess it will be easiest to start with an illustration. This should give sort of an impressionistic introduction to what is going on. So the canonical illustration of the Takens theorem is usually given by the Lorentz attractor. So here you see the Lorentz attractor, which is an attractor in R3. So each state of the system on the attractor is described by three variables, x, y, and z. So this is what we see on the left, and what we see on the right is the time series of the x coordinate itself. Okay, so there is some initial point which, as time goes by, it flows on the attractor, but we record only the values of the x observable. And the general question is how to reconstruct the picture on the right, the picture on the left from the picture of the right. So the data that we have is this one-dimensional time series, and we want to somehow try to reconstruct the original dynamics. And now what Takens theorem tells you to do is it tells you to do the following thing, which is this time-delayed embedding. So what you do is you draw a new picture where, as the original x coordinate, you just put the values of the x coordinate which you know, right? But as the y coordinate, what you do is you put the same values of the time series of the x variable, but shifted in time. Okay, so you fix some shift, capital T, and now as the y coordinate, you put this shifted values. And for let's say that we draw the picture in 3 dimensions. So as the third coordinate, we do the same thing, but just shifting in time twice. And now the Takens theorem, it tells you that if the dimension in which you perform this reconstruction, in which you build this model is large enough, then you can kind of expect that this object that you obtain after the reconstruction is, well, in nice one-to-one correspondence with the original system. So this way you get maybe an isomorphic model of the unknown original dynamics, which you obtain only from this one-dimensional data in this sense. And I will be, of course, more precise soon. And the most natural question is how many delays you need to do it. So what is the embedding dimension, the dimension in which you have to perform this reconstruction to have some good chance of indeed having a one-to-one correspondence? And Takens tells us that the numbers of measurements, or the embedding dimension which you have to take, is k, which has to be strictly greater than twice the dimension of the phase space. Okay, so if you know the dimension of the original system, then something larger than twice the dimension will suffice. Typically, that is for a typical observable. We will do. Of course, if you are familiar with non-dynamical embedding theorems like the Whitney's embedding theorem or Menger-Nobeling topological theorem, you see that this sort of results, they can be seen as dynamical versions of this non-dynamical embedding theorems, which tell you, for example, that if you have so the Whitney's theorem tells you that if you have a d-dimensional manifold, then typical smooth map into Euclidean space of dimension twice the dimension plus one will be a diffeomorphism on your manifold. Okay, so this is a sort of a dynamical realization of this sort of embedding ideal. Okay, let me start being a little bit more precise, but still not perfect. This is maybe mostly to set the note. So from now on, we will focus on discrete time dynamics. So we have, so T will be the map on the phase space X, and to the continuous time dynamics, this is applied just by looking at the fixed time map of the flow. And by H, I will denote the observable. So for a moment, an observable is just a function from X to R, and soon we will start imposing regularity assumptions on the dynamics and on the observables. And now the main question is whether, or the main object is the so-called delay coordinate map. So what you do is you fix the number of measurements K, and you look at the map phi, which I denote with indices T and H. So T the dynamics, H an observable. There should be maybe K here as well, because it depends on K, but to have a little bit less notation, let's skip K. So what it does is it assigns to an initial point in the system X a vector of length K, a K-dimensional vector, just of values of the observable along the first K iterates of X under T, right? And now the question is, so somehow the meta question is, under what conditions we can ensure that this delay coordinate map is injective for some K, okay? And then of course, the question is, what is the smallest reasonable K? And typical in your chosen class of observables for a typical observable H. Now, of course, you cannot expect this to hold for every observable. If you take a constant observable, then there is no chance for this sort of things. But it is reasonable to ask about typical observables. And now, what you see here is not really a proper theorem, but this is a sort of the meta statement of Takens type theorems, which look more or less the same in several categories. So the meta statement is like this. If the number, so there are two or three assumptions. So the main assumption is that K, the number of measurements, is strictly larger than twice the dimension of X. And then the conclusion is assuming that, so there are also two necessary assumptions for this sort of phenomena, that is injectivity of this delay coordinate map to hold, which are necessary. So first of all, the dynamics itself has to be injective. If the dynamics is not injective and Gluss points too early, then we cannot expect that applying observable will distinguish them. And second of all, we have to assume that there are not too many periodic points. What it means precisely in some case, I will show you in a moment, but it's easy to see that, for example, if you look at the set of fixed points, then injectivity of this map on the set of fixed points is the same as just injectivity of H, right? Because then this is a constant vector on the fixed point. So if the map would be injective on the whole space, so in particular on the fixed points, then it means that H itself, a one-dimensional observable, is injective on the fixed points, which means that it gives an embedding of the set of fixed points into the real line, which obviously cannot happen if the set of fixed points is too large, of too large dimension. So there has to be some assumptions on the periodic points. But once we have all of this, then this sort of theorems, they tell you that indeed phi is injective for typical observable. And the most famous result of this sort is the original one by Takens from the 80s, who proved this for actually for generic diffeomorphisms in the smooth category in C2. And then this was extended by Sauer, Yorke, and Kasdagli to the, the Lipschitz category. So to arbitrary compact subsets of Euclidean space with Lipschitz dynamics and Lipschitz observables, and this is the setting which we will follow. So in particular, their results apply to fractal attractors and stuff like this, unlike the original patterns. And what is maybe worth emphasizing is that this sort of results, they are not only mathematically interesting, but they also turned out to be interesting for people in applications. So indeed, this Takens theorem is invoked as a, well, theoretical justification for the technology of modeling or reconstructing unknown dynamics from time series. And up to today, you can find many papers which do it in many branches of applications. You can find it in ecology, in astronomy, for military purposes, and many others. Even, believe me or not, even for studying dense moves. There are papers which try to model dense moves, and they invoked patterns. Okay, so this was a sort of a crash course on the Takens theorem. So now let me tell you a bit what we do. So all the results that I will talk about are joined with Krzysztof Barański and Jonathan. So what we want to do is we want to study the situation in which there are self-intersections in the embeddings, which just means that the map phi is no longer injected. Okay, so it might happen that under this reconstruction, under the embedding, some distinct parts of the phase space, they get glued together. And the question is, this can happen whenever the assumptions of the deterministic theorems or the classical ones are not fulfilled for some reasons. But still, it is reasonable to ask whether you can get some reasonable sort of reconstruction, even having some self-intersections. And the way we approach it is through the probabilistic point of view. So our main observation, somehow the main philosophy behind our work, is that if we want to look at the situation in which apart from the system, we also have some probability distribution on the phase space. And now we no longer want to have injectivity on a whole space, but just on a set of full measure, which means that even if there are self-intersections, they are not too heavy. After removing a set of measure 0, according to whatever measure you have chosen, you don't see the intersections anymore. And then it turns out that you can reduce the number of measurements twice. This is somehow the main, again, maybe meta observation. And then this can be also applied to the question of predicting future values of the time series of the observable. So, of course, one of the main applications or usefulness of this Takens technology is reconstructing the original dynamics. But there is also another way that people are applying this sort of things, which is not really reconstructing the dynamics, but just trying to predict future values of this time series. Okay, if you assume you see a time series, you assume that it is generated by a deterministic dynamics through some observable, and then, well, whenever you have a good model of the underlying dynamics, then you can try to use it to iterate the dynamics further to do the predictions. But in this case with self-intersections, it might happen that even though you don't have a faithful model of the original dynamics, but maybe you can still do the predictions because they correspond to having a factor map rather than isomorphism with the original system. And combining all of this together, and this was the main force behind our main motivation for most of our work, is to solve, or at least mostly solve, predictability conjectures of Schroer, Sauer, Ott and Yorke, which conjectured in 98 in physical literature that indeed in this probabilistic context, the number of measurements should be possible to reduce the number of measurements twice and still have some reasonable predictability properties of the system. And I will also talk quite a bit about this. And finally, something that I will not have much time to talk about. But I just emphasize it here. So, okay, there are the Stackens theorems, and it's very nice. People use it as a mathematical justification for whatever they do. But what happens in practice is that you have a time series of an observable. So just you have a finite collection of numbers, and now you want to apply the Stackens theorems. But of course, you are in trouble because if the whole idea is that we don't know the original dynamical system. In particular, we don't know the dimension. So there is a couple of algorithms which try to maybe not estimate the dimension of the original dynamics, but just looking at your time series, you are trying to estimate a sort of an effective embedding dimension, which is maybe not really the one that comes from the Stackens theorem, but is good enough with some approximation. You have to fix some parameters and so on, but it's good enough to have a reasonable prediction properties of the system. And curiously, even though we know that the Stackens theorems formally are optimal, you cannot go below twice the dimension and still have the theorem, but somehow this effective embedding dimensions, they often tend, even for experiments with systems which we perfectly know, they seem to produce a lower embedding dimension which still have nice with good approximation, nice properties than the one predicted by the Stackens theorem. And it seems that what we prove, at least on a heuristic level, seems to give a mathematical or some justification for why indeed this effective embedding dimensions that are often observed are smaller than what the Stackens theorems tell you, and are usually closer to the dimension of the system rather than twice the dimension of the system. Okay, because in this algorithms you often want to have some good prediction properties only with high enough probability, which exactly puts us in this probabilistic system. Okay, so after saying all that, I can start being precise. So first I will formulate our version of a probabilistic Stackens theorem. And as you have already noticed, the crucial notion for this sort of theory is the dimension, right? So the dimension which we will use for the measures is the Hausdorff dimension. So here I recall what is the Hausdorff dimension of a finite Borel measure mu in the Euclidean space. So this is by definition just infimum of the dimensions of Borel sets of full measure. Okay, we neglect sets of measure 0 in all possible ways and search for the lowest dimension. If you haven't seen this before, let me note, dimension of a measure could be strictly smaller than the dimension of the topological support. So this is not just dimension of the support. And the second notion that we need is the notion of typicality for the observable, right? And the one that is commonly used for this sort of Stackens theorems is the notion of prevalence. So what is prevalence? This is supposed to be an analog of being of full Lebesgue measure, but in infinite dimensional vector spaces where there is no analog of Lebesgue measure, no locally finite shifting translation invariant measure. So what is prevalence? Okay, so let V be a Banach space, and now we will say that a set P is prevalent, so it's large, it's almost full in the space, if the following happens. If there exists a compactly supported Borel probability measure mu on V with the following property. So let me first say what's the idea, and then we can read the formal statement. So you want to be able to fix arbitrary vector in your space and then perturb it randomly according to this probability measure nu. And for the set P will be big if for every fixed initial vector, for almost every perturbation, we are back in P. Okay, and so the definition just says that for every initial vector, okay, W in V, for nu almost every E, this sort of additive perturbation is new. This is the definition. And as I said, this is an analog of sets of full Lebesgue measure in infinite dimensional spaces. And in Euclidean spaces of finite dimension, this is equivalent to being a full Lebesgue measure. And here is the theorem, the result. So X, this is the phase space of the system. This is supposed to be a compact subset of Rn. Mu, this is the Borel probability measure with respect to which we want to have this almost sure reconstruction of the system. T, the dynamics is assumed to be Lipschitz. And the main assumption is that K, the number of measurements, is strictly greater than Hausdorff dimension of mu. And now, for a prevalent Lipschitz observable, prevalent in the space of Lipschitz maps from X to R, there exists a Borel set XH of full measure on which the nice thing happens. And now what the nice thing is depends on the assumptions that we have. So the first one is the injectivity. So if we assume the dynamics to be injective, and recall, we need to assume that there are not too many periodic points. And in our case, not too many periodic points means that the Hausdorff dimension of the measure mu restricted to P periodic points is supposed to be strictly smaller than P. And this is for low periods, that is periods between 1 and K minus 1. And then for typical observable on a set of full measure, we get injectivity of this delay coordinate map, okay? So in this sense, there is an almost surely one-to-one correspondence between the model, the reconstructed model, and the original dynamic. Now, the second point is about this prediction properties. So if we do not assume the dynamics to be injective, and we don't assume anything about the periodic points, so we just assume that the number of measurements is greater than the dimension, then the map phi we can no longer guarantee it to be injective on a set of full measure, but at least we can, at least it becomes a factor map on a set of almost full measure. Okay, so we say that there exists a prediction map, which I denote by S. This will be this factor on a set of full measure, which goes from the image of the set of full measure to the image of the whole set, which has this property. Okay, it's just a factor. But the point is why we call it a prediction map, because you see what this map S does is the following. You feed into it a vector of length K of observables along the first K iterates of X, right? And what it gives you is the vector of observables, again of length K, starting at the iterate of X, which means that you have gained one more additional value of the observable in one step future of the system. So in this sense, it allows you to predict the future values of the result. Okay, and the natural question, so you see, this is a map which is defined on a set of full measure, and the natural question is what is the what can be said about regularity of this map, right? Which course, this is a natural question. You use it to make predictions of the values of the measurements, but if there is an error in measurements, you should know how it propagates. Well, we can at least say that it is under this assumption. So if K is greater than the Hausdorff dimension, then we cannot even guarantee it to be continuous. We can guarantee it at least to be continuous if K is greater than the Hausdorff dimension of the support of the measurement. Okay. And then we will soon talk about the conjectures, and the conjectures are also in some sense about regularity of this map S, but from a different point of view. Now, here we do not assume the measure mu to be invariant, but you need it to be invariant if you want to make sure that the set of full measure on which the nice thing happens is invariant under the dynamics. And you want it to be invariant under the dynamics if you want to, for example, be able to iterate this prediction map S. Okay, so so this is what invariance gives you. And this is all in the space of Lipschitz observables. But actually, the way the proof goes, which I'm not going to talk about, but I can just only tell you that so to prove the prevalence of nice observables in the space of Lipschitz maps, we have to construct this perturbating measure, this measure nu in the definition of prevalence. And the one that we get is supported in a finite dimensional space of polynomials in Rn, which means that essentially the same proof actually gives the result for typical CK observables, typical in the sense of prevalence. Okay, let's come back for a moment to this initial example with the Lorentz attractor. So, okay, the dimension of the Lorentz attractor is numerically estimated to be more or less 2.06. We've learned on the first day that it's very difficult to prove something rigorous about it, but at least there are numerical estimates which says that this is more or less 2.06, which means that for the original Takens theorem, actually, for this to be a good illustration of the theorem, this picture would need to be 5-dimensional, right? Because we need something much larger than twice the dimension. But you are fine with reconstruction in 3 dimensions if you allow this set of measure 0 intersection. So this is actually maybe an illustration of our theorem rather than the original. Okay, now let's talk about the conjecture. So these are conjectures of Schroer, Sauer, Ott and Yorke, and they are about they are about this question of predicting future values of the observable. So in terms of the delay coordinate map, we want to predict or approximate phi of tx from phi of x, and we want to do it with some bounds on the probability of seeing a large error in the prediction. And now let me define for you. Oh yes, let me define for you, following the authors, what they mean by the prediction error. So what we want to do is, okay, here is a formula, but maybe it's better to take a look at this very professional picture. So what we want to do is the following. We assume that we have some point y, which is a measurement vector, okay, of some initial point x naught, which should be drawn here, but it's not here. So there is a point x naught here, and what we know are the values phi of x naught, which is 1. So this is a vector in k-dimensional space. And now what we want to do is we want to take a look at all the possible measurement values which are epsilon close to y, okay? And among them, we want to see if we now look at their one-step future under the dynamics and then after projecting down to the reconstruction, how spread this epsilon ball will become under this process. So what we do is we take preimage of this ball under phi, iterate by the dynamics, and then project down. And now remember that we are in the probabilistic setting. So we don't want to just take a look at the set, but rather at the measure. So we define measure mu y epsilon, which is measure mu, which lives in the original system restricted to this preimage. And once we have this measure, we can push it forward by t and then by phi. This gives some probability distribution on the. So this is a we start with a conditional, so it's normal. So we have a probability distribution down here around phi of ty. And we ask, and the prediction error is by definition the standard deviation of this probability. Okay, so how spread are the one-step futures of epsilon good approximation of your initial measurements? So this is denoted by sigma phi of y epsilon. And now a point y will be called predictable if for this given y, as epsilon goes to 0, this standard deviation, so this prediction errors, they go to 0. So it means that at least in principle, if you make if you have a very good approximation of the initial point here, then you will have an almost unique prediction of the one-step future. Okay, and now this seems a bit abstract, but this is actually connected to a convergence of some specific prediction algorithm. You just feed it a finite time series, and it produces for you the future. This is the so-called Farmer-Siderovich prediction algorithm. And for ergodic systems, whenever you are given a point where this holds, then you actually get a convergence of this algorithm. And it is actually very simple because, and this is also something that you can estimate from a sample, because you see if you have a cloud of data in RK, then you just end, well, okay, if your trajectory is maybe typical and dense enough, you can look at all the values of the measurements that indeed land epsilon close to y. And then for them, you don't need to go back to this original system, which you don't know. You know the one-step futures just by sliding the window on the time series, right? So this is actually something that can be tested. And now, okay, now I will state the conjectures. And now to state the conjectures, I need two notions. So the first one, I probably don't need to talk about too much here. So the first one is a notion of natural measure. So the conjectures are stated only for a very specific class of measures for diffeomorphisms, which the authors call natural measures. So the definition is the following. We have X, the set on which the dynamics happens, is supposed to be a compact Riemann manifold. T is a smooth diffeomorphism. Lambda is a compact attractor with an open base of attraction B. By attractor, I just mean invariant compact set, which has an open base of attraction. And then a measure mu is called natural for the dynamics or for the attractor if for almost every initial point in the basin according to the volume, the orbit equidistributes according to the measure. So it's like a physical measure, but you want to have it on the set of full measure, not just on something of a positive measure. And the second notion is the notion of dimension. Again, dimension is crucial. And in the authors of the conjectures, they use the information dimension. So let me introduce it briefly. So this is also called entropy dimension, and this is notion of a dimension which is based on Shannon's entropy. So what you do is you take dm to be a partition of the Euclidean space, the most standard partition into dyadic cubes of side length 2 minus m, and then the information dimension is by definition the limit of 1 over m times the Shannon entropy of this partition dm with respect to the measure. Maybe assume for simplicity that measure is compactly supported, so the entropy is finite. So here is the formula. This is the Shannon's entropy of the partition, and this is of course provided that the limit exists. Otherwise, we have upper and lower limits. So now the conjectures. So there are two conjectures. So they are stated only for natural measures. So this is already a very strong assumption. Not all diffeomorphisms admit a natural measures, and the bound on the number of measurements, k, is that it is supposed to be strictly greater than the information dimension of the measurement. Okay, and then for typical observables, two things should happen. So the first conjecture is a weaker one, and it just says that if there are enough measurements in this sense, then almost every point is predictable. So at almost every point, we get this converges to zero. And now the second conjecture is about the speed of convergence in some sense. So what you do is you fix some delta, arbitrary positive delta. You look at the set of all points for which you see large error in the prediction. And large error means by definition that sigma is supposed to be greater than that. You look at all the sets and you look at what is the probability. So what is the measure of the set of points with large prediction error. And now by the first point, as epsilon goes to 0, this measure converges to 0. And the question is how fast? Well, the conjecture is that it should converge like epsilon to power k minus the information dimension. Okay, so we assume this to be we assume k to be greater than the information dimension. So this is some positive number. So we have some definite speed of convergence to 0. And this is unless there are no intersections. So if k is so large that the classical Takens theorems work, then actually for small epsilons, this will be an empty set and the measure will be 0. Okay. So here are our results, what we can say about the conjectures. So first of all, as stated here, the conjecture is not true. We construct a counterexample. And the problem is the notion of dimension. Information dimension is just a not good notion of dimension for this sort of embedding theorem. And we construct an explicit counterexample on a three-dimensional manifold with a natural measure for which these two things don't hold. However, we can say something positive. Conjecture one, so this first point, is true in much greater generality, that is, in the setting of this previous theorem for general measures, for general Lipschitz dynamics, as soon as we replace the information dimension with the Hausdorff dimension. So the Hausdorff dimension is the correct notion of dimension for this sort of problems. And in particular, so in general, there is no comparison. You can get both inequalities. However, if your measure is ergodic and the dynamics is Lipschitz, then the information dimension is an upper bound on the Hausdorff dimension. And it means that and the conclusion from this is that the conjectures, the first point of the conjecture is true as stated for ergodic measures, right? Because then this is a stronger assumption than K being greater than the Hausdorff. Yes. No. Well, it could be a Dirac mass, but then these questions are not very interesting because you only have 1 point and you look at embeddings of 1 point. But in general, yes, this is, well, the more complicated the measure is, the higher the dimension, the more difficult this thing is to achieve, right? But in general, there are, so in this general statement, the one in this second bullet, there are no other assumptions on the measure than just bound on the dimension. This is for very general measures. So this is conjecture one. About conjecture two. Well, here, again, we can prove that the upper bound in the conjecture, so the upper bound on the error probability is indeed what was predicted by the authors, as soon as we replace the information dimension with something even larger than the Hausdorff dimension. The Hausdorff dimension no longer works here for this more quantitative statement about the prediction errors. But if we replace it with the upper box counting of the support of the measure mu, then here we get an upper bound. Okay, and indeed, in general, this does not hold for the Hausdorff dimension. The upper bound doesn't hold for the Hausdorff dimension. But the example which we have so far is not in the class of natural measures. Okay, it is in this more general class of some measures for Lipschitz dynamics. So, well, so far we cannot say for sure that the upper bound is not true for the Hausdorff dimension in the class of natural measures, but definitely it is not true with the information dimension. Okay. Well, okay, so there was this previous result. Oh, yes. So if we assume that K is greater than the support of the Hausdorff dimension of the support of the measure mu, then we get this continuity of the prediction map. This, however, well, this doesn't tell us much about the speed of the convergence of this probability errors to zero. So yeah, so the Hausdorff dimension of the support of the measure mu in general is also not good. Okay, so I'm close to finishing. So let me tell you what we actually more precisely prove. So as I told you, this is an upper bound in the conjecture. So we don't really get K minus the dimension as the exponent, but we get something arbitrarily close to it. So if you fix some small error in the exponent theta, then then there is a constant which depends on delta and theta such that this inequality holds. And actually we prove something even stronger, that is not only the set of points where the prediction error is large bounds like this, but actually just the set of all the points for which there exists a single brother who projects epsilon close under phi, but after the dynamics, they get delta apart. Okay, so this is something even stronger. Let me just say you one word about the proof, and it's literally one word, and this word is transversality. So all of this is a suitable version of transversality, which has to be well adjusted to this delay coordinate maps and so on. So basically, what you want to prove is that whenever a bad thing. So first of all, there is this perturbation measure. So you fix an observable, and then you introduce some space of parameters according to which you do the perturbations, which in our case are polynomials. So we are just choosing coefficients of the polynomials in the perturbation. And then what you want to prove is whenever a bad thing for you happens, and the bad thing is, for example, phi of x, let me simplify it. A bad thing is phi of x being equal to phi of y, but phi of tx not being equal to phi of ty. So this is about existence of this prediction. Then you want to show that whenever this bad thing happens to you, then at least in the parameter space, when you start perturbing your observable, then with some positive speed, you get away from the set of observables on which the bad thing happens, and this boils down to a maybe a bit complicated analysis of how finite parts of the orbits can intersect and what does it tell you about the observables and so on. Okay, so I guess I will finish here. These are the papers where the results are from. Thank you very much.
Thank you. Thank you very much for a predictably interesting talk and for ending without delay. Are there any questions?
Yeah.
So is it known if the conjecture is known for like another diffeomorphisms and its SRB measures?
Oh, that's a good question. I don't know. We haven't studied too many particular models. So far, we are at the level of proving general theorems. Definitely, the counter examples that we have are not in this class.
Thank you very much.
Thanks. No, not much. We don't have much control of C delta. The proof uses Borel-Cantelli and stuff like this, so it's not constructive in the sense of knowing what C is. No. C delta is this. Yeah.
More questions? Hold on. Oh, well, now you have to ask a question. Great. Well, again, thank you very much for this most interesting lecture. We have some time between now and lunch. Maybe that's a good time to remind you that there are interesting posters in the hallway, which you can peruse on the way over. And that ends